Our topic is Cauchy's integral test and problems on Cauchy's integral test. What does Cauchy's integral test says? Here, if fx is positive, defined for x greater than or equal to 1, positive, monotonically decreasing. Two conditions on fx are there. Fx is positive, monotonically decreasing function of x, and f of n is an for all n. F of n is an. Then sigma an and 1 to infinity fx dx either both converge or do not converge. See, the use of integral test is we test the improper integral for convergence. 1 to infinity, this is called improper integral, and the primitive can be easily obtained here. Primitive means integral fx can be easily obtained. Then we say that 1 to infinity fx dx converges if limit t tends to infinity 1 to t fx dx exists, and we test the convergence of 1 to infinity fx dx. Suppose it converges, this sigma an converges, and if it diverges, sigma an diverges. And I explain the proof later, but I consider problems on this. See, the conditions important here. What is the condition? Fx is positive, monotonically decreasing, and we take f of n is an. Then integral 1 to infinity fx dx, sigma an from 1 to infinity behave alike. Say problems on this. First one, test the convergence of sigma 1 upon n log of n raised to p. Log of n raised to p. Now we write f of x is, let fx is 1 upon x log of x raised to p. What is p here? P may be any integer here. P may be any integer. Let us discuss what is the value of p and whether it converges or diverges. For what values of p it converges. Suppose fx is 1 upon x log x raised to p. We take fx as this. Then what is the first condition here that you have to verify? Fx is positive for x greater than 1. Fx is positive in 2 to infinity. Fx is positive for x greater than or equal to 2, because when x is 1 it is not defined. We have to consider from 2 to infinity. Fx is positive and monotonically decreasing, because log of x and x is in the denominator. As x increases, 1 upon x log x raised to p decreases. Therefore fx is monotonically decreasing in 2 to infinity. Now therefore what is the Cauchy's integral test? Therefore by Cauchy's integral test, integral 2 to infinity fx dx and sigma n is equal to 2 to infinity an either both converge or diverge. Either converge or diverge. What is an? An is 1 upon n log of n raised to p. An is 1 upon n log n raised to p, and fx is 1 upon x log x raised to p. Only replace n by x here. 1 upon x log x raised to p. Then first condition is satisfied here. What is that? Fx is positive and monotonically decreasing in 2 to infinity. Now what happens? How to apply Cauchy's integral test? Cauchy's integral test says that 2 to infinity fx dx and sigma 2 to infinity an either converge or diverge together. Now we consider this one, integral f of x dx. What is integral f of x dx? 1 upon x log of x raised to p. with respect to x. Now suppose p not equal to 1. P is not equal to 1. Then what happens? If you do log x as p, log x as t, it is like this. I explain how to integrate this, how to obtain the primitive. Suppose p is not equal to 1, then we take log x is equal to t here. Therefore 1 upon x dx becomes dt. So integral becomes dx by x is dt. So dt by t. What is dt by t integration? Log t. No, what is this? Integ by t raised to n, it is correct? Because suppose p is not equal to 1, take log x is t, 1 upon x dx is dt. So it is dx by x is dt, t raised to p it is. What is integral t raised to p? T raised to p minus 1 by p minus 1. P is not equal to 1. Therefore it is minus p plus 1 by minus p plus 1, correct? I think you followed this one. Integration by substitution here. It is therefore log of x raised to 1 minus p upon 1 minus p not equal to 1. And it is equal to, suppose p is equal to 1, then what happens? When p is equal to 1, it becomes dt by t. Same substitution, dt by t is log t. Log of log x when p is equal to 1. P is equal to 1. So two cases are there. P not equal to 1. Integral dx by x, integral fx dx is log x raised to 1 minus p by 1 minus p. When p is equal to 1, it is log of log x. Therefore, now we consider integral 2 to infinity fx dx. We consider 2 to t first, because when do you say that 2 to infinity fx dx converge? If limit 2 to t fx dx, t tends to infinity, exists. So 2 to t fx dx is, it is, what is this? It is log of t raised to 1 minus p upon 1 minus p minus log of 2 raised to 1 minus p upon 1 minus p upon 1 minus p. If p not equal to 1, two cases are there, and it is log of log t minus log of log 2 when p is equal to 1. I think this is clear. What is an integral test? Cauchy's integral test. We have to consider the convergence of 1 to infinity. In this case, for 1 it is not defined, so we take 2 to infinity fx dx. If 2 to infinity fx dx converge or diverge, sigma an also converge or diverge. They are alike. These two are alike. Cauchy's integral test. Now we consider the convergence of this. How to test the convergence of this? First we take 2 to t fx dx. It is this. For p not equal to 1 is this. P is equal to 1 log t minus log of log 2. Now we take limit of this as t tends to infinity. Limit 2 to infinity or 2 to t fx dx as t tends to infinity is equal to, it is equal to infinity when p is equal to 1. Because here I take p is equal to 1 first. Log infinity is infinity when p is equal to 1. So when t tends to infinity, it becomes infinity. Now suppose p is less than 1. P less than 1, then also it becomes infinity. P less than 1. Why it becomes infinity? Because when p is less than 1, this log t raised to numerator, it remains in the numerator. P less than 1, it becomes infinity. When p greater than 1, this log t, limit depends on log t here because it is constant. Log t, when p greater than 1, it comes to denominator. Log t comes to denominator, and log infinity is infinity. 1 upon infinity is 0. This becomes 0. It becomes log 2 raised to 1 minus p upon p minus 1 when p is greater than 1. When p is greater than 1, or we can write 1 upon log 2 raised to 1 minus p. 1 upon log 2 raised to 1 minus p. Anyway, this becomes finite, that is limit t to infinity, t tends to infinity, 2 to infinity, fx becomes finite only when p greater than 1. P less than or equal to 1, it is infinity. We say that this integral 2 to infinity fx dx, 2 to infinity fx dx diverges when p is less than or equal to 1. Converges p greater than 1. Therefore, 2 to infinity fx dx converges when p greater than 1. Therefore, sigma 2 to infinity an 1 upon n log n raised to p converges when p greater than 1. P greater than 1. And integral 2 to infinity fx dx diverges if p is less than or equal to 1. Therefore, sigma an also diverges when p is less than or sigma an means this diverges. So we can apply Cauchy's integral like this. Cauchy's integral test like this. So the given series converges when p greater than 1. P greater than 1. Where p converges if p greater than 1 and diverges if p less than or equal to 1. You follow now? So in Cauchy's integral test, convergence or divergence depends on the improper integral, and you know how to test the convergence of improper integral. I think first problem is clear for all of you. Second is test the convergence of sigma n e raised to minus n square. Sigma n e raised to minus n square. So in all the 4 tests, ratio tests, practical comparison test, root test and D'Alembert's ratio test, we have not came across this type of problem, n e raised to minus n square. In this case, we apply Cauchy's integral test. Let an is n e raised to minus n square. Therefore, f of x is x e raised to minus x square. Now, whether it is positive, in 1 to infinity we take, is it positive? Fx is positive for all x greater than or equal to 1. Can you realize or did you understand this one? Because e raised to minus exponential function is always positive or may be equal to 0. E raised to minus x square. 0 when for infinite value of x. E raised to minus x square is positive. X greater than or equal to 1. This is positive. And monotonically decreasing it is. It is monotonically decreasing. Why it is monotonically decreasing? X divided by e raised to x square. And this e raised to x square increases more rapidly than x. Therefore, as x increases, denominator increases. So x by e raised to x square decreases. So it is monotonically decreasing for all x greater than or equal to 1. Therefore, integral 1 to infinity fx and sigma an 1 to infinity are alike. By Cauchy's integral test it is. Cauchy's integral test. Now we have to test the convergence of this. Consider integral x e raised to minus x square dx. How to integrate? We take x square is t. Therefore, x dx is dt by 2. So it is e raised to minus t dt by 2 because x square is equal to t. This is the substitution. 2x dx is dt or x dx is dt by 2 e raised to minus t. What is the integration? 1 upon 2 minus e raised to minus t. Therefore, 1 to t fx dx. Fx dx is 1 to t is minus 1 by 2 e raised to minus t minus e raised to minus 1. It is 1 to t. One to t, this one, e raised to minus t e raised to minus 1. Correct? But here we have to substitute. What is this? Minus 1 by 2 e raised to minus x square. Because we have taken x square is t here. We have to substitute here. X square is t. So 1 to t fx dx is minus n square minus e raised to minus 1. Is it correct? First we have to obtain the integral. It is called primitive. Primitive can be easily obtained. Therefore we can apply integral test. Primitives are very difficult to obtain. Then it is not convenient to apply this test. Now primitives can be easily obtained. Minus half e raised to minus x square. So 1 to t is, what is 1 to t? 1 to t is minus t square. Am I correct here? 1 to t. Correct, 1 to t. Therefore, limit 1 to t fx dx as t tends to infinity is minus 1 by 2 0 minus e raised to minus 1. So 1 upon 2e it is. 1 upon 2e. Because when t tends to infinity, e raised to minus t square is 0. Minus is there. Therefore 1 upon e raised to t square. It becomes 1 upon infinity is 0. E raised to minus 1. So 1 upon 2e finite. So what's your conclusion? This improper integral converges. Therefore, integral 1 to infinity fx dx converges because we have finite value here, 1 by 2e. By Cauchy's integral test, sigma an. What is sigma an? Sigma an is n e raised to minus n square converges. I think you followed the solution here. How to apply Cauchy's integral test, or when to apply the Cauchy's integral test, that is also important. Next, apply Cauchy's integral test. To discuss the convergence of sigma 1 to infinity 1 upon n raised to p, where p is positive. This is a standard series and we have discussed this one in detail, and also we have taken the use of this series in many problems. While comparing, we have taken this as auxiliary series. You know the nature of this series. Sigma 1 upon n raised to p, when it converges, if p greater than 1 converges, p less than or equal to 1 diverges. Now we have proved this one by comparative test. We have proved this one. But Cauchy's integral test can also be applied to prove this. See, now you know that the mode of examination, it is MCQ, multiple choice questions. This is apply Cauchy's integral test to discuss the convergence of this is 5 mark question. Same question can be converted to objective multiple choice question. How do we can convert? We can convert like this. By Cauchy's integral test, sigma 1 upon n raised to p converges if p converges if p greater than 1. 4 choices will be p greater than 1, p is equal to 1, p less than 1, fourth one none of this. Always that fourth choice is kept so that all the 3 answers are incorrect. By mistake, suppose all the 3 answers are incorrect, then fourth none of these will come to help for question paper setters will come to help. But in this case, p greater than 1, it converges. So for this question, how we can convert this into objective type? By Cauchy's integral test, sigma 1 upon n raised to p 1 to p converges if 4 choices are p greater than 1, p less than 1, p equal to 1, none of this. Your choice is then p greater than 1. But for descriptive question, we can apply Cauchy's integral test to discuss the convergence of this. How do you apply that one? Here, what does Cauchy's integral test says? If fx is, what is an here? An is 1 upon n raised to p, p greater than 0. Therefore, let f of x is, then f of x is 1 upon x raised to p, where p is greater than 0. P greater than 0, yes. P greater than 0. Now, what is the condition in Cauchy's integral test? Fx is positive and monotonically decreasing for all x greater than 1 or equal to 1. For all x greater than or equal to 1. I think this you can easily understand. Monotonically decreasing it is, and it is positive. That is the condition of Cauchy's integral test. What does test says? If sigma an is positive term series and f of n is an, f of x is an, f of n is an, yes, f of n is an, then sigma an and integral 1 to infinity f of x dx are alike. Now we have taken fx as this 1 upon x raised to p. First condition is satisfied, monotonically decreasing and it is positive. Therefore we can apply integral test. First we take, suppose p is not equal to 1. P not equal to 1, then integral, I write this as in. Suppose in is 1 to n fx dx. Instead of t, I have taken n here. In the previous two problems, I have taken 1 to t, then t tends to infinity. I have taken 1 to n here and denoted by in. But here also we take n tends to infinity. If n tends to infinity, this exists, then we say that this converges. So in is 1 to n fx dx, p not equal to 1, then it is 1 to n 1 upon x raised to p, it is equal to, what is 1 upon x raised to p? X raised to minus p plus 1 by minus p plus 1 from 1 to n. So it is 1 upon 1 minus p x raised to 1 minus n upon x raised to 1 minus n. What is the x is n raised to 1 minus p minus 1 raised to 1 minus p. When it is p not equal to 1. N raised to 1 minus p minus 1 raised to 1 minus p. Now, when it is p not equal to 1, suppose p greater than 1, then limit n tends to infinity is that we require now. If In becomes finite when n tends to infinity, this In converges. Correspondingly, sigma In converges by Cauchy's root test. Limit n tends to infinity when p greater than 1. Suppose p greater than 1, what happens? It is this one up becomes p greater than 1, this goes to denominator, and n tends to infinity, this becomes 0. So we get it is equal to 1 upon p minus 1. 1 upon p minus 1, finite. This you have to understand, this is important. When p greater than 1, the value of p important now. P greater than 1, this goes to denominator, because p greater than 1, 1 minus p is there. 1 minus p becomes negative. Negative index go to denominator, and in the denominator n tends to infinity means 1 upon infinity is 0. So we have only this one. What is that? Minus is there. Therefore I change it to p minus 1. 1 upon p minus 1, which is finite. Therefore In converges, hence sigma In also converges. Sigma In means 1 upon n raised to p, converges. So we have obtained same thing here, p greater than 1 converges. Suppose p less than 1, I take p is less than 1, then limit n tends to infinities. Yes, now it is important. When p less than 1, then what happens? This is In here. P less than 1, this remains in the numerator. 1 minus p is positive, numerator. And this tends to infinity. So, tends to infinity. Therefore, In does not converge or diverges to infinity. Therefore, sigma In diverges to infinity. So, p less than 1, it diverges. Greater than 1, converges by integral test. Now one case is that, what is that? P is equal to 1. When p is equal to 1, p is equal to 1, In is 1 to n 1 upon x dx. It is log x from 1 to n. So log of n minus log 1. But the log 1 is 0. So log n it is. And limit n tends to infinity becomes infinity, because log of infinity is infinity. So what's your conclusion? By Cauchy's integral test, sigma n means sigma 1 upon n raised to p diverges. So diverges when p is 1, diverges when p less than 1, say diverges p less than 1, converges when p greater than 1. This we have already proved, and we have taken use of that one for comparison. But how we can prove that one or test the convergence of that auxiliary series using Cauchy's integral test. This is Cauchy's integral test. I hope the solution, all of you understood the solution, and also you can easily apply this concept to integral to any series. One more problem I take, and if possible I try to complete that one. Apply Cauchy's integral test to test the convergence of sigma 3 to infinity 1 upon n log n into log of log n raised to p, where p greater than 0. P greater than 0. Now, an is this. This is an. And therefore, f of x is 1 upon x log of log x raised to p. Now, suppose p is equal to 1. Two cases are there, p equal to 1, p not equal to 1, because the integrals are different. When p is equal to 1, this becomes log of log x, fx is, or in is integral 1 to n dx upon x log x into log of log x. log x, and its integration is log of log x, because see here, why it is log x, because when p is equal to 1, this is log x. If you take log x as t, this as t, and this becomes dt. So 1 upon t dt. What is integration 1 upon t? Log t. T is this from 1 to n. So it is log x means log n minus 0, because log x is log 1 is 0. Log 1 is 0. Is it from 1? It is not 1. It is from 3 to infinity, because for 1 it is not defined at all. It is monotonically decreasing in 3 to infinity. First condition. What is the condition? Monotonically decreasing and positive in 3 to infinity. Therefore, we take from 3 to infinity. It is minus log of log 3. Log 3. And as n tends to infinity, in tends to infinity. Therefore, when p is equal to 1, this in diverges. Therefore, when p is equal to 1, this series diverges. P is equal to 1 diverges. Suppose p not equal to 1. We consider p is not equal to 1, this case. Then in is integral 3 to n dx by log of log x raised to p into log x into x. This is the integral. Now suppose that p is not equal to 1, then integral is different. And p is equal to 1, it is log of log x, correct? Log of log x. P not equal to 1, it is log of log x raised to p minus 1 plus p upon minus 1 plus p. Minus 1 plus p from 3 to n. From 3 to n. Correct? Log of log x raised to minus p plus 1 upon minus 1 plus p from 3 to n. It is therefore 1 upon p minus 1 log of log x raised to 1 minus p minus log of log 3 raised to 1 minus p. Am I correct? Raised to 1 minus p. From 1 to p not equal to 1. Yes? P not equal to 1. Now, suppose p not equal to 1 here, p greater than 1. Then what happens? P greater than 1, it becomes in the denominator, it goes to denominator. This is important because it is a constant. It goes to denominator. When p greater than 1, in tends to 1 upon p minus 1, or becomes 1 upon 1 minus p log of log 3 raised to 1 minus p when p greater than 1. So finite. So what happens? Finite. Therefore this in converges. Therefore that given sum converges. Given sum converges when p greater than 1. Previous case was p is equal to 1, it diverges. Not equal to 1 important. Greater than 1 converges. And p less than 1. Then what happens? I take p less than 1. P less than 1, what happens? This remains in the numerator. This is in the numerator. And n tends to infinity becomes infinity for greater p less than 1. P less than 1. Therefore, p less than 1, in tends to infinity. So this diverges. In diverges. Therefore, by Cauchy's integral test, given that is sum sigma an diverges. To go through the video again, we can apply Cauchy's integral test like this. Now proof of this is on the left. Then I go to the last topic, that is alternating series. Okay, thank you.